Hello, everyone. Thank you for coming. Today, I'll be talking about fast algorithms for matching markets beyond stability. And this is a joint work with my advisor, Professor Yuri Fanza. First, let me give you a motivating real-world example. So every year in New York City, about 90,000 students will enter about 300 public high school programs. And the Department of Education needs to figure out how to assign these students to school programs in a fair way. So currently, this is how it's being done. A central government will collect the following informations. First, every student will rank the schools in order of preference. Similarly, every school will also rank the students in order of preference. In addition, every school will also submit a quota, which is the maximum number of students the school can admit. So for simplicity in this talk, we're just going to assume that every school has a quota of 1. So once the central government collects all these informations, it needs to find an assignment that is fair according to some metrics. And this metrics is usually done through the concept of stability. So a matching or an assignment is stable if there's no unmatched student-school pairs that prefer each other to their assigned partner under the matching. And if such a pair exists, this is called a blocking pair of the matching. So let me demonstrate this idea more concretely through an example. Here I have 3 students and 3 schools. And for example, student 1 prefers school A the best, followed by school B, followed by school C. Now let's consider 2 matchings. The first one is the matching that I put in box. And I claim that this matching is not stable. In particular, it admits a blocking pair, which is the pair that I put in blue. So students 3 and school A. So imagine the central government ended up using this matching as the final assignment. What could happen is that students 3 and school A will just talk to each other and say, you know what, let's just form a pair on our own, and let's not respect what the central government is telling us to do. And this is clearly not something we want. On the other hand, the matching which I marked in red is a stable matching. And you can check yourself that it indeed admits no blocking pairs. So in the seminal work by Gale and Shapley, they show that stable matchings always exist, and one such stable matching can be found efficiently by the deferred acceptance algorithm. So in practice, besides school choice, this model is widely used in many other markets, and here I listed a couple of examples. And the reason that this model is so attractive is because it sort of has the full package. So first, it is envy-free. And in this context, it just means that it has no blocking pair. It is also strategy proof, which means no one has the incentive to misrepresent their preference relations. Also, it is computational efficient, as I mentioned earlier. In fact, the deferred acceptance algorithm runs in time linear in the number of student-school pairs. And lastly, all stable matchings are Pareto optimal, meaning that if you want to improve for one agent in the market, you have to hurt someone else. But stability does have a couple drawbacks. So note that stability is a symmetric concept, meaning that it puts no distinctions between schools and students. But in the school choice context, schools are often perceived as commodities to be distributed to the students. As a result, there have been many algorithms, mechanisms, or concepts proposed in the literature to favor students over schools. Here I listed a couple examples. And the goal of these mechanisms are usually to find a matching that is Pareto optimal for the students. So if you go back to the previous example, and let's consider these 2 matchings again. As it turns out, the matching that is not stable is actually Pareto optimal for the students, which means if you want to improve for one of the students, you have to hurt someone else. On the other hand, the matching that is stable is actually not Pareto optimal for the students. In fact, you can swap the partners of student 1 and student 2, and that will end up giving you the matching in the box. So in this talk, I'll be focused mainly on the latter 2 mechanisms, which are efficiency-adjusted deferred acceptance mechanism and legal assignments. So I would just like to point out that the efficiency here does not come from computational efficiency, but rather from Pareto efficiency, which is another name for Pareto optimality. So first, let me give you the idea behind EADAM. So recall that the goal is to find this Pareto optimal matching, which I put in box. So what EADAM will do is that it will ask students 3 to give up on school A. And if students 3 consent, we could just remove this pair from the instance. And now this matching becomes both Pareto optimal for the students as well as being stable. And of course, EADAM doesn't just go there and randomly ask students to give up on some schools. It actually look at the steps of the deferred acceptance algorithm to figure out which student you should ask to give up on what school. But that's too much details, which I'm not going to go into. Next, let me introduce legal assignments. I'm going to first introduce the ideas behind legal assignments, followed by the formal definition and the results that's already shown in Ehlers and Morrow. So continuing on with the previous example, it has 5 maximal matchings, and I can construct a blocking diagram where each node represents a matching, and I put an arc from matching A to matching B if A contains a matched pair that is a blocking pair for matching B. Now I want to partition the matchings into 2 sets, a good, like one set being all the good matchings and the other set being the bad matchings. So to start with, the stable matching is a good one because it's not being blocked by any other matching. And then we can see that these 3 matchings are bad ones because they're being pointed to by our good matching here. And lastly, for this blue matching, I claim that it's also a good matching because it's only being blocked by these 2 bad matchings. So altogether, I have a partition of the 5 maximal matchings, the good ones and the bad ones. And here's the formal definition. So a set of assignments is a set of legal assignments if it satisfies both internal stability as well as external stability. So internal stability just means that any 2 assignments in the set do not block each other. So in this case, these 2 matchings are not pointing to each other. And external stability means that every assignment that is not in the set is being blocked by someone in the set. So in this case, these 3 matchings are all being pointed to by these matchings here. And it is shown that the set of legal matchings always exists and it is unique. Moreover, it forms a distributive lattice, and the student optimal legal assignments can be found by EADAM because the output of EADAM, when assuming all students consent, is exactly the same as the student optimal legal assignment. So I would just like to point out that the distributed lattice property is actually a property that is also satisfied by the set of stable assignments. Now for our results, we showed that legal assignments can actually be represented by stable assignments, but in a legal subgraph or subinstance. And we can find this subinstance in this time complexity, which is the same as the time complexity for the deferred acceptance algorithm. So a direct consequence of our theorem is that algorithms in the literature that are designed for stable assignments can also be extended to legal assignments with the same time complexity. And a couple examples are the following, such as finding all stable pairs, enumeration of all stable assignments, and finding a maximum weight stable assignment where the weight is on the student and school pairs. Another consequence of our theorem is that EADAM can be implemented with the same time complexity as the deferred acceptance algorithm under one special case, which is when all the students consent. So we didn't just stop here. We actually tweak a little bit about our algorithm, and we show that this is actually true for any set of consenting students. We run a couple computational experiments on randomly generated instance. And here we have the x-axis being the instance size and the y-axis being the runtime. These 2 lines are existing algorithms in the literature for EADAM, or one that is proposed by Kasten in his original paper, and the other one is a simplified version proposed by Tang and Yu. And this purple line is our algorithm, and the gray line is the deferred acceptance algorithm that is included just as a reference. And as can be clearly seen here, that our algorithm runs a lot faster than the other two algorithms in the literature. We also conducted some computational experiments on instances that has the same size as that of the New York City. And here, just one example where I assume that all the students are consenting. Again, this is the deferred acceptance algorithm, and this is our algorithm, and this is the simplified EADAM. So our algorithm is basically the same running time-wise as the deferred acceptance algorithm, and our algorithm is a lot faster than simplified EADAM. So now let me give you a very high-level idea of our algorithm and how we use the ladder structure to construct our fast algorithms. So here I plotted a ladder structure being formed by all legal assignments, where each dot represents one assignment, and the red ones are stable assignments, and they form a lattice on their own, and the blue ones are the legal assignments that are not stable. So efficient algorithms for stable matchings relies heavily on the fact that you can move inside the stable matching lattice quite freely. So for example, if you're standing at this stable matching, you'll be able to see all the trading cycles that preserve stability. And these trading cycles are represented by the 3 solid lines here. However, you also have another trading cycle, like marked by this dashed line here, which only preserve legality. But this trading cycle is not readily seen. So the idea of our algorithms is to repeatedly identify and remove illegal edges. And an illegal edge is simply a student and school pair that is not in the legal sub-instance. And once we remove an illegal edge, we'll be able to see this trading cycle. And then we can remove another illegal edge to see another trading cycle. And then we can remove another one to find another trading cycle, and then we can just keep on doing it until we remove all the illegal edges, and in which case we construct our legal sub-instance. And once we're in our legal sub-instance, all these assignments become both legal and stable, and now we can freely move inside this stable matching lattice. So here's a summary of our results, which I'll put on the last slide. You can also find our paper on arXiv, and thank you for your attention.